Hello and welcome to the Room of Lives. I am your host, Neil. Today we will hear Dr. Aaron Zimmerman, professor of physics at the University of Texas at Austin and researcher at the LIGO gravitational wave detector, give a public talk about gravitational wave astronomy. He gave this talk as part of an outreach weekend, so it avoids technical language and is quite accessible. Whereas in regular astronomy we use light from celestial objects to learn about them, in gravitational wave astronomy we do that using gravity waves. Gravity waves are extremely weak, and Dr. Zimmerman describes the device that has been built at LIGO to detect them while screening out fake signals caused by events such as a storm or a truck driving by. If you enjoy visiting the Room of Lives, consider donating Ether, DAI, or other Ethereum-based coins to abranil.eth. That's abranil.eth.
All right, thanks everyone. Can you hear me okay without the microphone? If my voice ever gets too quiet, please give a shout. I tend to be a loud person anyway, so I worry that when I put on the mic, I just blast your ears. Much like Professor Gordon's talk, feel free to interrupt with questions, and I'll also try to take a pause in the middle of the talk at sort of the halfway point so that we can have a little bit of questions if they arise. While I still remember, I thought it was really interesting that Professor Gordon took a moment at the end to talk about more practical things. I'll try to also do the same at the end. Let me just say that my very first semester in university, I was pretty unhappy, and I think it definitely had something to do with moving to a totally new environment, having some things be not quite the way I expected them to be, and not having many friends. So it may sound a little corny, but I think what Professor Gordon was saying is actually really great advice. Make sure to address all aspects of your life when you're in university and beyond. So today I'm going to tell you about gravitational waves, which is a topic I research in. And I'm going to have to explain to you what gravitational waves are first, and then I'm going to explain to you why gravitational waves are a very exciting new way for us to come to understand the universe around us. So Professor Gordon's talk was about how physics meets biology and organisms. My talk is about how physics meets astronomy and our study of the universe. So first I'm going to tell you about gravitational waves. So if you've had a physics class so far, you will have learned a little bit about the force of gravity, about how orbits work. I've drawn for you a picture of the Earth going around the Sun, not quite to scale, I have to admit. And you may have heard this story already. What gravity is a universal force between objects which have mass. And if you have a planet like Earth, which is moving with some velocity, and there's some attractive force to the Sun, that attractive force tries to pull the Earth towards the Sun, but of course the Earth is already moving, so the effect of the force is to change the velocity, and so a moment later, the velocity has turned a little bit due to the force, and the force has also changed direction to continue to point to the Sun, and so this will continue and the Earth will travel happily in its orbit as the force of gravity adjusts its velocity. This theory of gravity was one of Newton's many contributions, but one of his greatest contributions to our understanding of physics. And furthermore, it is a theory which is actually quite good. It explains really well the orbits of the planets around the Sun, motion of bodies here on Earth, the motion of stars within our galaxy. It is not quite the correct theory of gravity. If you really look very carefully, or you go to very extreme situations where gravity gets very strong, what you find is that Newton's theory of gravity is not quite perfect. It's a good approximation, but it's not the full story. Now, you may have heard the resolution to this story was Albert Einstein's theory of relativity. And it really is a completely mind-bending re-envisioning of the universe we live in. What Einstein told us is that we don't want to think about gravity as being due to forces pushing on objects. Instead, we have to realize we live in something known as space-time. And furthermore, this space-time within which we're immersed can have some kind of non-trivial shape to it. It's pretty much impossible for us to visualize what that really means. So what we physicists like to do when talking about and trying to visualize space-time's shape and structure is we often rely on a little cartoon here that's sort of like imagining space and time as a trampoline. Okay? So we imagine space-time as a sort of flexible sheet or membrane, and when I place a massive object in that membrane, it causes the trampoline to curve. Okay? And now we can imagine how the curvature of space-time itself can change the motion of bodies without requiring a force between the two bodies. But instead, we imagine that if I take the Earth as like a little ball on a trampoline that I've placed a bowling ball, and I roll it, well, of course, the curvature of the trampoline will deflect the motion of the Earth. And if you tune this just right, you'll get the Earth to go around in a circle as it tries to move in a straight line. And it's no longer moving in a straight line simply because the structure of space-time itself is curved. This is Einstein's theory of general relativity, and it describes the sort of truest theory of gravity that we know, and it has a lot of amazing implications. One implication we can sort of understand simply by taking this analogy of the surface of this trampoline a little bit further, and we can ask ourselves what happens when a massive object is now moving around on this sheet of space-time. And you can imagine what the answer would be. As an object moves around in space-time, it is causing the curvature of space-time, but as it moves, the fabric of space-time needs to respond to that motion. And just like rolling something across a trampoline, you can imagine sends out vibrations through the surface of the trampoline, the motion of massive objects through space-time sends out ripples in the fabric of space-time itself, sort of like the ripples on the surface of a pond, and these spread out away from the objects and travel out through space. These are known as gravitational waves, these ripples in the very fabric of space and time itself. Now, this picture might give you some sense, maybe some intuition for why massive objects moving around in space-time might send out these ripples in the fabric of space-time. But your next question should be, okay, what do these waves do when they pass through something? What is their effect on objects as they move through them? This little movie I'm about to show you.
Question.
Yes.
So the ripples of the waves, the amplitude, does it represent the time or space?
That's a great question and not actually easy to answer, but I'll try to answer it with this movie. What the amplitude of the waves in that picture is meant to represent is it's meant to represent how strong of an influence those waves have on objects they pass through. Okay? So the waves are waves in both time and space, but it's very hard to actually, in any reasonable sense, without just working with the mathematics of it, to really turn that into some concepts that are easily understandable. However, understanding how those waves push on objects, that's something we can understand physically and intuitively. So I'll focus on that question. What happens when the waves pass through objects? So in order to show you what happens when the waves pass through objects, I've got this movie. This movie serves several purposes, which means it's kind of a complicated movie, so I may have to show it twice, and I'm going to try to explain it as well as I can. First of all, what we have here is a little tabletop experiment. It's a very famous experiment known as an interferometer. What it does is I take laser light from a laser, and it hits a half-silvered mirror, a mirror that reflects half the light and allows half the light to pass through. So this single source of laser gets split into two pieces. I send them down some tube or some tunnel, some distance, where it meets a mirror, reflects back, meets a mirror, reflects back, and then combines again at the mirror. This is just the experimental setup. Now, what does a gravitational wave do when it passes through objects? As I start to play the movie, we will see, we imagine a gravitational wave which is going to pass down through the top of this experiment, so into the screen. And as it passes through, what it's going to do is it's actually going to push on all the objects. It's going to stretch out the distance between the laser and one mirror, and then compress it periodically. It's going to do exactly the same, but in an opposite phase to the other mirror. So that's what happens when a gravitational wave passes through an object. Now I'm going to pause this movie and go back a bit. Oh, well, I didn't manage to pause it, so you'll have to watch the movie again. So this stretching and compressing of objects, or stretching and compressing of distances, this is the effect that a gravitational wave has as it passes through an object. So in answer to your question, the amplitude of those waves is actually going to be how far apart these mirrors are pushed and drawn together. Okay? Now, this setup is nice because it also shows you how we could measure the effect of this gravitational wave. Because the reality is, this gigantic motion of the mirrors and the laser beam is incredibly exaggerated. Gravitational waves are in fact incredibly ghostly and weak. They have almost no effect on objects they pass through. So in order to actually detect them, we need to detect really, really tiny changes in the distances between objects. And this interferometer experiment actually gives us a very powerful way of measuring those changes in distances. And that's what gets explained in the second half of this movie. So I will pause it right around here. What's being visualized here is, remember, the laser beam went down two paths and gets recombined at the mirror. You may have heard in your physics class that light itself is also a wave, right? So light itself is also a wave. So we're representing it here with peaks and troughs, little crests, just like the wave on the surface of an ocean. And you may know that when you combine two waves together, the two waves are going to add together and have an effect. So when the waves add together so that the peaks of one wave, the one going, say, down the left track, and the troughs of the other wave, say the one going down the other perpendicular track, when they combine so that peak hits a trough, they're just going to cancel out. So what's the effect? What is the light going to look like there when the two waves are canceling each other completely? There's no light. So light as a wave can interfere with itself, and if you add together two waves of light that are destructively interfering, that cancel each other out, you get no light at all. Okay? Now, as the wave pushes on the mirrors, what happens is that the light has to travel a little further down one length than it does down the other length. And so it might execute a larger number of oscillations as it moves down that path and comes back than it did just a moment before. And so a very slight change in the distance light travels is going to shift around these peaks. And so a very small shift in the distance between the mirrors can cause the light to go from destructively interfering to constructively interfering so that the peaks overlap. And what do you think happens then? There's light. You detect some light. Something wrong?
No, so very quick. So every time you point at some bit of laser, it makes bonk sound.
Wonderful.
So I've muted it, but you may need to unmute it.
I will need to unmute it.
Okay.
Yeah, I was wondering what that sound was.
Right. It's this beautiful setup we have here. Somehow when you hit the laser, it makes the sound.
So you can see that in order to measure a gravitational wave, even one that changes the distance between these mirrors just a fraction of the wavelength of light, you can set up this interferometer and then monitor the light coming out one end. And as it goes bright and dark and bright and dark, this allows you to monitor very tiny, minute shifts to this interferometer. Now, just building a simple interferometer like this, with a simple laser pointer, only slightly better than this, and some simple mirrors that don't actually cost that much money, you can actually measure, you can build an interferometer that will measure changes that are a fraction of the wavelength of visible light. Does anyone have a sense of how long that is? What is the wavelength of visible light?
400 nanometers.
400 nanometers, that's right. 400 nanometers is roughly several times the size of an atom, right? So with just a simple tabletop experiment, you can measure distances that are hundreds or tens of atoms in changes in the distances of mirrors that are hundreds to tens of atoms in size. So really, really microscopic. It's really an amazing thing. However, for a gravitational wave coming to us, the most intense, strong gravitational waves coming to us from a distant part of the universe, from systems that I'll explain in a minute, those waves, the very strongest waves we can imagine, they will move mirrors on the surface of the Earth less than 1,000th the size of a nucleus of an atom. So just building one of these tabletop things doesn't get you there. You're millions of times off where you need to be. And so, in order to try to detect these gravitational waves that are predicted by Einstein's theory, we need to do something a bit more than just build a small tabletop experiment. Instead, we build a massive experiment. these are known as the LIGO and Virgo interferometers. Okay, the LIGO and Virgo are these large scientific experiments. They took decades to plan and build. So the LIGO experiments in particular were conceived of and planned in the 70s and 80s. They were constructed and run at an initial phase in the 90s and then the 2000s. And then they were completely torn down because what they achieved was really, and something that was incredibly sensitive, but still not sensitive enough to detect those tiny, tiny motions that gravitational waves cause. So what's going on here? These are two large physics experiments. One is in Hanford, Washington. This is actually an old nuclear testing site, so it's a big empty plot of land that no one wants to really live in. People do live nearby. And then the other experiment has been set up in Livingston, Louisiana, in the middle of a swamp. Okay? What's happening here is this center station is that center station that I showed you in the other cartoon. This is where there's essentially a laser and a monitor of light. That laser gets split and sent 4 kilometers down to a mirror that's sitting at the other end, and then it bounces back and comes back. And the other half of the laser light is sent down another arm, which is another 4 kilometers in length, and then that comes back. And by making the interferometer longer, we already enhance our ability to detect these minute changes due to the fact that the longer the wavelength goes, the smaller the shift in distance will actually move those peaks around. That's still not good enough. What's actually done is you place another mirror here and here so that the laser light actually bounces back and forth down this 4 kilometers about 300 times. And then you bring it back together to try to register. On top of that, you have to carefully control every aspect of this experiment. Once you've set up this bouncing back and forth, souped-up interferometer, it is really sensitive at detecting anything. A truck drives by, it's going to shake the mirrors. A storm in the Gulf of Mexico causes significant noise in the experiment here in Louisiana. Okay, so they measure waves crashing against the shore hundreds of miles away. Okay, that's something they detect in their experiment, and it actually swamps out, potentially, the signal that they want to see, the gravitational wave signal. Yeah?
Do gravitational waves have minute changes in time also? Like it doesn't...
Yeah, that's an excellent question. They can, yes. They do, yes. It turns out that the way that this experiment is designed, it specifically tries to probe the changes in space. There are other experiments, maybe at the end I'll get to one, which actually does the other thing. It can measure the change in time. But you set this experiment up to try to be sensitive to the change in the distance between mirrors. That's an excellent question. Yes?
Why do they oscillate the light?
That's a great question. So the oscillation comes about kind of from this picture. So notice that as these move around, they're going through themselves kind of a periodic motion. So the system's returning to its original state again after a little while. So the waves they produce need to go through a cycle. So they tend to go up and down. And so the wave signal you expect to see is going to go up and down, up and down, up and down periodically. And so as the waves then travel through the experiment, the waves are going to push and pull, push and pull, push and pull on the mirrors. Is that the question you were asking?
I think it's the wrong word. Why do they send the light back and forth a few times?
Great question. So coming back to this movie, I'll skip forward to closer to the end so that we can see it. Okay, the effect you're trying to get here is a shift between a peak and a peak. So imagine we start with a peak and a peak. And now what happens is that the laser light contained in each of the arms might have, let's say, 1,000 cycles coming back and forth. And so if I shift that just a little bit, then a pull of that 1,000 cycles a little bit over will pick up a whole other part of a cycle here. Now, instead, if I fit many, many cycles back and forth, that same pull might pull multiplied by 100th. So if I send this back and forth many times, then as I shift the mirrors very slightly, then the amount that this actually shifts relative to the other gets enhanced by that same factor, how many times I bounced it back and forth. Does that make a little bit of sense? It's okay. Ask again if you're confused afterwards. I can try to explain it in a different way. Now, together with these two LIGO experiments, there's a third experiment in the two LIGO experiments. There's a third experiment built essentially the same, just slightly smaller, that is built in Europe, near Pisa in Italy. And this is the Virgo detector. So these are large physics experiments. They take decades to build. They're manned by teams of hundreds or even 1,000 scientists who work together both to build, design the experiment, and to analyze the data coming out of it and make sense of what it means. And as I said, it took decades for these interferometers to be built in the first place. And then in the mid to late 2000s, when they had run for a while at their initial sensitivity without detecting any gravitational waves, they needed to be upgraded. So every component was sort of torn out and improved and replaced, and they were brought to what we call their advanced configuration, which meant that they were going to be much more sensitive to these ghostly gravitational waves passing through the experiment. And almost as soon as these were up and running in their advanced state, they detected the very first signature of gravitational waves. And I'm going to play you a movie, and now we're back to the boinks because it's an audio movie. I'm going to play you a movie which illustrates this detection. And for this, I've got a graph that I'm going to show you. And so I'm going to quickly explain to you what you're going to see in the graph before I play you the movie. What we're going to show you is we're going to show you the evolution of the signal in time. And what you're also going to see is how the signal changes in frequency. Okay? So what you're going to see here is a spectrogram. I don't know if anyone here is really into music, or maybe playing around with GarageBand or whatever on your iPad. But if you take a chunk of music and you analyze it, you often look at a spectrogram, which tells you what are the tones in the music at a given time and how they change, right? So music at a given tone might be a given frequency, and of course you have a whole combination of tones that make up the sounds you hear. So what I'm actually going to show you is essentially a sound file. These waves, as they pass through the mirrors and they push and pull on them, that light that changes, bright, dark, bright, dark, bright, dark, that gets recorded. And the way that that's recorded is essentially an oscillation in the fabric of space-time that we're recording. And it turns out that the oscillations are actually happening in the hertz. Okay, so hertz is per second. So between 10 and say 1,000 cycles per second is actually the speed of this signal. So it's actually quite fast, right? But it actually also happens to be the same range of frequencies that your ear is sensitive to. So we like to take these recordings of the vibrations of space-time and play them back for you as sound. Of course, they're not sound, but it's nice to record them and play them back as if they are sound, because it gives you an impression. So I'll show you the spectrogram, which is the way to visualize the sound, and I'm also going to play the sound for you. Now, this first detection happens at the very low hertz, and it's fast. So all you're going to hear is like a really deep bass thump, okay? So what we've done is we're going to play that thump for you a couple times, and then we're going to artificially increase the frequency. I think we more than double the frequency so that it moves into a range your ears are more sensitive to so that you can hear it a little better. So let's give this a shot. So that was it. That was a thump coming to us from I've already forgotten. About 1 billion light years away. I think a little closer than that. Okay? That thump was registered in those detectors. It was over and done with just like that. And you heard, of course, at the true frequency, very low bass, and then that up at the higher frequency, you could maybe hear a little bit more of a detail. The signals started to go whoop. So they increase in loudness, the waves get stronger, and they increase in frequency for a reason we'll see in just a moment. And again, on the spectrogram, you can see how the signal is, there's just a lot of noise in the detector, and then the event happens all of a sudden, and the event starts with a signal at low frequencies and sweeps quickly to high frequency, and then it's done. Okay? Everyone good? Want to hear it again? Yeah.
How do you know that it came from 100 billion light years away?
That is an excellent question. Let me play a different movie first, and then I'll try to answer your question. All right. So what did this come from? How do we know that it came from a large distance away? How do we know what this was? So first of all, we heard these quote unquote, these gravitational waves in the machine. Then what do? Well, it turns out that people have been theorizing for decades about what kinds of objects in the universe make gravitational waves and what particular sweep of sound, so to speak, we should hear when those waves pass through the Earth. And there's a lot of information contained in this little sound file. And by teasing it apart and using our very best theories about what happens, we can figure out what produced this burst of gravitational waves and answer questions like how far away was it? And it turns out our best understanding of physics and of this signal tells us that this was made by two black holes which were orbiting each other. Those black holes were incredibly massive. They had about 30 times the mass of our own sun each. Okay? They whirled around each other at a fraction of the speed of light, like 10% of the speed of light, in a tight orbit, before finally colliding together. That incredibly rapid motion of super-dense objects is what generates such strong gravitational waves that they can travel such a long distance to get to us. And it's by modeling that system and knowing how strong the waves should be when it gets generated, and then measuring how strong the waves were when they get to us, that we can figure out how far away they were. So first I'll talk about black holes really quick. You may have heard about black holes before. They're one of the most mysterious, cool sounding things in physics, which is why I studied them. I was so excited by the idea of black holes that I had to learn more about them. This is a still from the movie Interstellar, which the advisor of my advisor actually was the scientific advisor on this movie. So he did everything he could to try to ensure that the physics in this movie was as accurate as possible. So this is a pretty good depiction of what a black hole might actually look like. Now, black holes, we call them black because they don't emit light, okay? And what's happening with a black hole is that it's an object that is so dense, the gravitational fields around it are so strong that even light can't escape if it gets too close. What that means is there's a certain place around the black hole from which light doesn't escape. We call it the event horizon. And from this surface, we don't see any light, so it would look totally black, okay? So we can't actually see black holes in light because they don't emit light. Instead, in this picture, in order for you to actually visualize the black hole, what's shown is a black hole with a thin disk of hot gas, glowing gas around it, okay? And then the gravitational curvature around a black hole is so strong that this disk, it wraps around behind, and the light from that gets bent. The gravity is so strong it bends the path of light. So this is actually the disk behind the black hole. So what this picture really is it's just a black hole with a single thin disk. But you see around the backside of the black hole because the light gets bent over top and the light gets bent under bottom. Okay? So we're talking some really exotic things here. Okay, objects that are so dense that the curvature of space-time bends the path of light so that you can see behind an object. That's a single black hole. We also believe that black holes come in pairs, that they can be paired up in the universe, sort of like the way the Earth orbits the sun, but much, much closer. And we can try to understand what happens when we put two black holes in orbit around each other. That's a very hard problem to solve. So in order to solve problems like that, we have to reach for supercomputers. Okay? So we actually get computers to do the hard math for us to simulate what would happen if we put two black holes in orbit. And this is one of the things I work on in my research, is running these kinds of simulations to understand black holes in orbit. And so I'm going to play for you one of these simulations. So this is just a computer simulation. And there's a lot of things going on in this simulation, so I'm going to talk as it plays. These are two black holes in orbit. Their properties have been chosen so that they agree with the signal that we saw for that very first detection of gravitational waves. Right now they're in a tight orbit near the end of their time orbiting each other. And as they orbit, they emit gravitational waves, which causes them actually to slowly draw together. They orbit closer and closer. What you're seeing here is that trampoline I talked about. The curvature of the surface is meant to represent the strength of space-time curvature, the strength of gravity. The color's kind of interesting. The color represents the slowing down of time. Another effect of curving space-time is time slows down. At this point, the orbit's getting very dynamic and complicated. The black holes are getting very close together, and we slow down the movie for dramatic effect, not because this actually gets any slower. We slow it down, and when things get really exciting, the two black holes will merge together. They'll combine to become one single bigger black hole. And we pause the movie there, just so that you can see that really exciting moment. That final black hole quickly relaxes down to a quiet state, and those gravitational waves I talked about that were produced, they spread out through the universe at the speed of light. And after they travel for 1.3 billion light years, they eventually reach the LIGO detectors to be detected as that thump that you heard. Any questions about that?
So that's the only way we can detect gravity waves, right? That's like the only thing strong enough to.
Yeah, so the LIGO and Virgo detectors are the only things that are right now sensitive enough to detect these gravitational waves. And these sorts of systems, these extreme systems, are the only thing that produce waves that are strong enough to detect. Now, there are some other systems that people are trying to detect waves from, but so far they haven't been successful. In order to detect these gravitational waves, they're already so incredibly weak from these kinds of systems. It takes a system that has extremely fast motions and extremely dense objects. So there's another kind of system we've seen in gravitational waves that I'll talk about in a little bit, but it shares one property in common with this black hole system. It's made up of objects that are incredibly dense, moving incredibly fast. And those are the only objects so far which can generate gravitational waves that we can detect. Yes?
How common are black hole mergers?
That is a great question. So these thumps, they're happening all the time, okay? It's just that most of them happen so far away that the signal's too weak to reach the detector. I'm trying to, I can give you an answer, but it's not necessarily an answer that's so useful, and it might take me a few minutes to convert it. But let me just say that by measuring how often these signals arrive at the detectors, we have a rough sense of how often black holes are colliding with each other in the universe. And in the whole universe, it's on the order of 100,000 a year. In the local universe, it's less. Okay? Yeah.
So what happens if there are two black holes merging and then there's another set of black holes merging and they're really close together?
That's a great question. So I'll answer first that, and then I'll say whether we expect such a thing to happen. So if there were multiple objects that were orbiting, there are in fact places in the galaxy and in the universe where you can get clusters of objects doing complicated things like two of them are orbiting, and then that pair is further orbiting. That can happen. And what would happen is that you might have one set merge, the other set merge, and then the final thing would be a pair, which in principle could possibly merge, but there's a few things that kind of spoil that. For one thing, it's not obvious from this movie I just showed you, but in that final burst when the things come together and emit waves, it actually gets a recoil most of the time, a very strong kick, which might break that system up and prevent it from further merging. That kick can be quite strong. It can be a hundredth or a tenth the speed of light. Okay? So, not a tenth, a hundredth the speed of light, let's say. Now, we don't usually worry too much about that possibility, though, because these merger events are actually fairly rare, and those black holes on the scale of the universe are actually extremely close together. So to get multiple black holes kind of close together and close to each other is kind of like a very unlikely thing to happen. How close were these things to each other? Well, each of these black holes, I said they were 30 times the mass of our sun. That means that they are 80 kilometers across. Sorry, 70 kilometers across. Okay? Very small for such a massive object. And you saw from the video that they're not that far from each other. So that whole system might only be 200 kilometers in size. Compared to the size of the universe, that's like a tiny little point. You had a question.
Yeah, this reminds me a lot of the early microwave measurements that happened in the last century. And I think I just figured the answer out to I was going to say, is there any problem like background radiation where you're picking up?
Another great question. I was actually going to talk a little bit about the microwave background, and then I removed it from this talk. Let me just say that the neat thing about gravitational waves is that they, for the same reason that they have very little influence on the detector, very few things influence them. So they're not absorbed much by the detector. They don't deposit a lot of their energy in the detector. These gravitational waves travel through the universe basically undisturbed. So we don't have to worry about something distorting them coming to us, and we also don't tend to have to worry about other sources of gravitational wave noise which might cause problems. However, the big thing we have to fight against is the terrestrial noise here on Earth, right? So in order to make that detection, we had to sort of already make sure to screen out the motion of the ground, right? The motion of the ground caused by a truck driving by a little ways away. Things like lightning bolt strikes can cause fake signals in these detectors because the electric and magnetic fields travel around the Earth and cause just the tiniest disturbance in the detector. So every tiny disturbance in these detectors can cause problems and fake signal and noise that we're trying to dig under to detect these real signals. Yeah?
you have like particle situated near the black hole, like where they merge the waves, like the noticeable?
Absolutely. Yeah. So the question is sort of like, well, how close could we be till we actually felt these waves? And it's a question I haven't worked out in a little while in detail, so I've forgotten it a little bit. But basically, the closer we get to these objects, the stronger the waves become. And so, if right now the mirrors in the LIGO experiment are being moved 1/1000th of the size of an atomic nucleus, if I move a billion times closer, so instead of standing at a billion light years, I stand at a light year, I would magnify the signal by a billion. Now, that's still not enough to really have an effect, but you could get a billion times closer still. And you really could get in a situation where you could potentially physically feel some effects. In fact, whether or not you really feel effects on your own body would depend a little bit on the details of the system and how close you can really stand. All right, I'd better move on. John, what's my time so far?
15 more minutes.
Okay, that's not nearly enough time, but there have been a lot of great questions. So I told you a little bit about gravitational waves and what makes them. Now I want to give you the idea of where this field is going. So an enormous amount of effort went into building these detectors. And this detection of gravitational waves has fulfilled kind of one of the last untested parts of Einstein's theory of relativity, confirming our best understanding of gravity. And that alone is very spectacular. It also taught us that these black holes are out there in the universe. This pair of black holes we couldn't have detected any other way. They don't emit light, they just emit gravitational waves. So seeing them in gravitational waves was the only way to know that these systems were out there in the universe. Okay? Now that's exactly then what we want to try to use gravitational waves for. We want to do a new kind of astronomy. So if you think about astronomy, this may be what you think about. Okay? This is a visual image of the full sky, right? That then has been put in a panoramic view. The bright cluster of stars here, that's our own Milky Way galaxy, right? We sit in a galaxy which is a cluster of stars. It's a very thin disk, so all the action is going on here, and I guess I could turn off the sound. But you also, I'm sure, know that there are other wavelengths of light out there, okay? So visible light, red through violet, is only one narrow range of wavelengths and frequencies in which we have something we would know as light or electromagnetic waves. And there are many other kinds of light that we can imagine being emitted. So in particular, radio signals are another flavor of light, so to speak. They're an electromagnetic wave which is much longer in wavelength and much lower in frequency than the visible light. The same is true for microwaves, for infrared radiation. That's the radiation that is emitted by objects that are around room temperature. They glow in the infrared. And then as we go to more intense energies and ever shorter wavelength, we start to get into things like ultraviolet radiation, X-ray radiation, and then finally at the highest energies of all, the shortest wavelengths, we get gamma rays, right? Which you can often think about as single particles of light with extremely high energy, banging into things and possibly tearing stuff apart. So it was realized over the course of the last century that we can do astronomy not just with visible light, as we've done for thousands of years, but also with all these other forms of radiation. So by pointing radio telescopes at the sky, we get a totally different image of our universe, okay? You can still see our Milky Way galaxy, but there are these weird features extending out. These are clouds basically where electrons are moving around in magnetic fields and producing radio waves. And there are other point sources of radio emission which turn out to be gigantic black holes in distant galaxies that are eating a lot of material and have intense magnetic fields around them. So you learn a lot by looking in a different wavelength. The same is true if we look in gamma rays. I'll talk, maybe I don't have time actually, but I would have talked a little bit about the Fermi Gamma Ray Telescope. Gamma rays are so intense, they interact so strongly that they don't make it through our atmosphere. So gamma ray astronomy couldn't be done until we had satellites that we could put up above the atmosphere, and then these things could start to receive gamma rays from the universe. And you get a totally different view of the universe. You see many of these little pinpricks. These are bright systems. Probably most of these are all in our own galaxy, where there are incredibly energetic processes happening, often associated with black holes or other dense objects. But we learn an entirely new, we get to see an entirely new side of our universe where we see in a different wavelength. The idea then for gravitational waves is, well, if we can learn so much about the universe by different wavelengths of light, what if we look at the universe in a completely different way? We see things that are invisible in all of these wavelengths of light. That leads us to this idea that we want to do gravitational wave astronomy, astronomy using gravitational waves. And this is a field that is completely in its infancy. Okay? 2015 was when that first detection was made. It's now 2019. So it's only been a field that's been happening for a few years. And this is what we've got so far. In addition to the very first detection of gravitational waves, I think that is probably this system. We have seen we've seen a total of 10 bursts of gravitational waves coming from the merger of black holes. And on this graph, you've got the black holes placed in size and in position according to how massive they are. So a lot of these systems all tend to be pretty massive. The black holes tend to be 20 to 40 times the mass of our own sun. We've seen a few systems that are a little more lightweight, a mere 7 times the mass of our sun in the black holes, okay? But this is starting to fill out a picture of systems of what kinds of black holes are out there. And gravitational wave astronomy is going to try to take a census of all the black holes that are out there in the universe. But gravitational wave astronomy can do something else too, which leads me to this little thing down here, which is another kind of system that we can detect in gravitational waves, and is in many ways the most spectacular of all of these discoveries so far. Before I talk about that, I can show you a little movie. This is another, like the simulation I showed you before, these are a set of computer simulations of black holes orbiting each other, which are consistent with all the signals that have been seen so far. You can see the variety of sizes and properties of these systems that we've seen so far for the black holes. And this is a visualization put together by an undergraduate student at Cal State Fullerton. So just reminding you that even as you get into university physics, or whatever you do in university physics or not, there are opportunities for you to do interesting research projects, even at that early stage. All right, so let's get to that little one at the bottom. This was a very different signal than the other ones, and I'm going to play it for you just like I played the other signal, and you're going to notice right away that it's a bit different. Did you hear that? So there's two things that were different about this. First of all, the noise level, the background noise level was a lot louder. That's because this signal is just a lot weaker than the other one. You can see here the track in the spectrogram. It's much, much longer and much, much thinner than that other signal. It also happens to be lower in amplitude. So this was a quieter signal, but it went on for a very long time, and it had a very clear sweep upward in frequency. And in fact, in terms of pulling this signal out of the noise, this is by far the most significant of all the detections we've seen, way more than the one you saw before. Okay, and that comes from the fact that it's so long and clean in this, even if it's lower in loudness, lower in amplitude. Okay? The fact that this goes on for a very long time is an indicator to us of the masses of this system. The longer the signal lasts inside of the LIGO detectors, the longer we can see it for, the lower in mass that system is. And so let me try to show you another movie. If we look at the wave itself, the up and down motion of the wave in time, these are what those other signals look like. It's a wave that goes up, down, up, down, up, down, up, down, up, down, and then it stops. Okay? You can see the very first one only was seen for a few cycles of the wave. Some of the other ones that I showed you, they go on for a bit longer because they're lower in mass. And now I'm going to show you the signal that you just heard. While the other ones go on for up to 20 or 30 cycles, this one was observed to go on for hundreds and hundreds and hundreds, and in fact thousands of cycles. This movie goes on for a minute, so I'm never going to finish actually playing the whole movie. I never have in a talk. It just goes on and on and on and on. So a very different kind of signal. Yes?
So that signal detected, what year was that?
That was in 2017. So we call them, we give them names based on when we see them because we're very unimaginative astronomers. So this was observed in 2017 in August on the 17th. Yeah. Well, it's better this way. If you let particle physicists name things, they go a little bit crazy, and you get particles like neutrinos and leptons and neutralinos, and it's just a disaster. I'm sorry, John. I don't know.
I take offense.
Particle physicists should have hired a advertising team, I think, to name things. Yeah.
Quarks are great.
Yeah, quarks are good.
Is there a theoretical limit to how long in time the signal can be?
That's a great question. So what limits how long we can see the signal for is the frequency over which LIGO is sensitive. LIGO and Virgo are sensitive too. So remember I said it's in the audible band. It goes from about 10 hertz to 1,000 hertz. It turns out that a signal, these signals, they orbit for much, much longer than we can actually detect them in the detectors, okay? These signals could have been going on for 1 million years, and we don't know because until they increase their orbital rate to a frequency that we can begin to hear, they're not picked up in the detector. So in principle, if you could get a system very low in mass and very close to us, yes, we could see it for quite a long time. Yeah.
Did Virgo detect the neutron star merger?
Yeah, that's a great question. In fact, that's what's one of the things that's so special about the neutron star merger. So the LIGO detectors were running starting in 2015, and they made the first detections independently. And then in 2017, the Virgo detector joined the effort. They joined actually in August. And in this month of August, we detected 4 systems, 5 systems, 4 or 5 systems. I lose count. So they joined at a very lucky month. So they were actually able to participate in a lot of things. And as I'll get to in just a minute, they also were able to help in the observation of this system. I guess I lied to you about having time afterwards. But I guess we've had a lot of questions during. All right, so what was it that made this system? This system was not produced by 2 black holes in orbit around each other. In fact, the system, the components of the system had such low masses that we think what they were are these things called neutron stars. Neutron stars are just about as exotic as black holes, okay? Neutron stars are the dense remnants left over when a star finishes off its life and explodes in a supernova, but is not quite so massive that it collapses to form a black hole. What you're left with is a ball of pure neutrons and protons, basically an atomic nucleus, but the size of Austin. But these things are about 1.4 times the mass of our sun, and they're about 10 kilometers across. A teaspoonful of these things weighs a ton, is a common thing that's said about that. Also, a teaspoonful of neutron star matter is actually extremely unstable. Unless you're compressing it down with intense gravitational fields, it is extremely radioactive and it is going to explode outward. Okay? And that's actually key for what I'm going to talk about next. So I don't have the time to talk about the rest of these things, but the neat thing about these being neutron stars is that neutron stars, unlike black holes, they're made of stuff that can emit light. And so unlike the black hole detections, this particular system, 2 neutron stars colliding, can emit both gravitational waves and it can emit light throughout the electromagnetic spectrum. So skipping ahead to the punchline, because LIGO and Virgo were all operating, we were able to locate in the sky where we thought this system where we thought the system was when the 2 neutron stars collided. Okay? It actually only gives you a fairly large swath of the sky. Roughly speaking, it's sort of about that much of the sky. So it's actually a pretty big area. But astronomers were waiting for this opportunity, and they sprang into action. We sent out an alert within an hour or so, saying, actually we sent an alert faster than that, but we sent out this map about an hour later, saying, hey, we think it happened over there. And they all ran to train their telescopes on it. And basically, the moment night fell over Chile, where there are some really great telescopes and some really great astronomy going on, people took this picture, this little spot. It wasn't there a few nights before, this little blue spot. This is a true color image. This glow is that radioactive fireball from the stuff that got knocked off the neutron stars when they collided together. And that radioactive fireball gets hot and glows. And a few days later, notice it's a lot dimmer and it's a lot redder. That's because the fireball's cooling down and dimming and eventually goes away. So you only have a little bit of an opportunity to catch this fireworks going on. So this will be my last movie and then I'll stop. This is an artist's impression, not even a computer simulation, just an artist's impression of this entire event. We have the 2 neutron stars, which are going to be in tight orbit, collide, and then there's going to be a lot of fireworks. Some of that fireworks makes that signal I just saw. Some of the other fireworks generate signals in the gamma rays and in the radio waves. And this is way more epic than the other movie I showed. It's got a better soundtrack. So they've collided, and here comes the radioactive fireball, which we actually imaged. This is a representation of the gamma rays, which were also seen, eventually giving way to radio waves, which were also imaged. This is a production of NASA. NASA has a much better production budget than I do, and they make much better movies than I ever could. And actually, I think I'd better just end it there. I was going to tell you a little bit more about the future, what's up ahead for us. But the future, let me just assure you, we're going to build even cooler detectors. We're going to make the detectors even better. We're going to see even more black holes and neutron stars. And we're going to learn a ton of things about the universe. We've already learned a lot about the universe from these detections, but we're going to learn even more. So I'll stop there and take some questions. Some more questions.
Can two different gravitational waves interfere with each other?
Yes, gravitational waves interfere just like light interferes. The thing about gravitational waves is that since these events that cause strong gravitational waves are very rare and short-lived, it's not expected that we have to worry too much. But in fact, something that is true is that we see these big events that are very strong, but throughout the universe there are many systems which are emitting at a much lower level all the time. So the Earth is bathed in gravitational waves which are interfering with each other. And in fact, there's a big effort going on within the LIGO and Virgo communities to try to detect that bath of interfering waves that are passing through us all the time, but at such a low level that it really just seems like noise in the detectors. Yeah?
How are LIGO and Virgo oriented with respect to each other?
Oh, I wish I had a picture. So, I have chalk here. I'm never going to draw Europe very well, so please forgive me. So, LIGO Hanford is up here in Washington State. LIGO Livingston is down here in Louisiana, and they're actually oriented very similarly to each other. So each of these is an L, and one of the L's is sort of inverted with respect to the other L. That means actually that they receive gravitational waves in a very similar way. I don't quite know the orientation of the Virgo detector in Italy. I guess I can add Italy down here. But it's a different orientation entirely, which is helpful because it detects the waves in a slightly different manner. And so that gives us a little bit more information if we're seeing the waves sort of from two different perspectives.
I have another question. How
Yeah.
do you get the length so exact, the 4-kilometer arm length?
That's a great question. So we don't actually have to get the 4-kilometer arm length so exact. What you do is you build the 4 kilometers as exact as you can, and then you carefully set up the interferometer and tune it by shifting the mirrors around just slightly so that you get it in exactly the state you want it to be, and then you compare, as the gravitational waves travel through it, how that changes from your tuned state. So you don't have to be so precise. What you have to be able to do is you have to be able to control and tune the interferometer once you've built it. It doesn't have to be precisely 4 kilometers down to like a nanometer. Yeah?
So you said the detectors were upgraded in the 2000s?
That's right.
Is there other plans to upgrade them again?
So right now what we're doing is we go through cycles. So we build and upgrade for a year, and then we run for a year to actually try to detect signals. So we've just actually finished a cycle of upgrading the detectors to make them more sensitive. And starting tomorrow or Monday, we will begin the third campaign of trying to do observations. And as time goes on, we hope to continue to improve the detectors, and eventually in about a decade maybe, this all depends on whether people can find money to do this, build entirely new detectors.
You mentioned the difference between the black holes and the neutron stars. I know the black holes were like 20 to 40
Yeah.
solar masses. Neutron stars, would you say 1.5?
Neutron stars the ones we've seen are about 1.3 times the mass of our sun, so these were about the same.
Couldn't we then detect waves from like very close binary systems?
Absolutely. So everything generates gravitational waves. So if there's a planet orbiting around our nearest neighbor, Proxima Centauri, that generates gravitational waves. But first of all, it generates waves that would be very, very low in frequency, once per year instead of once per second. Right? So that's one problem with detecting that. You have to find a system that can generate high enough frequency waves. It turns out that that means actually quite rapid motions of objects when we're talking about astronomical scales. So it's very hard to find objects that move fast enough to generate these waves.
Binaries, not very far away.
White dwarf binaries. So white dwarfs are a different type of dead star. They're much larger than neutron stars. It turns out that those therefore cannot be seen by LIGO. They're too low in frequency. Even when they're touching and orbiting each other, they're moving too slowly to make gravitational waves in the frequencies we would see here. Detect. Other questions? Yeah.
The gravitational wave discovered in 2015
Yeah.
was a billion years ago.
Right, good. So we know that gravitational waves travel at the same speed as the speed of light. And so that means, of course, that it takes time for them to get to us. So as with anything in astronomy, the further away we're seeing an object, actually the earlier in the universe's history we're seeing the object. So the first gravitational wave event occurred about 1.3 billion light years away. Therefore, it happened about 1.3 billion years ago.
Why do they travel at the speed of light?
Sorry. Einstein's theory predicts that they travel the speed of light, and now we've measured that they do. Sorry, you had a question. No? Are you sure? No one back there. I saw a hand go up. You have a hand?
So you talked about the ways that the signals at Virgo and LIGO could be contaminated by terrestrial stuff.
Yes.
Is there any automated way to cancel for this, or do people have to sit and manually decide this wasn't it, this wasn't it?
So there is a little bit more manual decision making than we'd like, but the reality is that everything is very automated. So the detectors are measuring things all the time, and we've created computer codes which continually ingest the detector data and try to decide all the time, is there a gravitational wave signal going on? Those computer codes have had to be coded up in such a way that they can distinguish, as best we can, terrestrial events that are not gravitational waves from real gravitational wave events. And this is crucial because there's stuff going on all the time shaking the detectors. We need to distinguish a vibration the detectors do to something on Earth from something coming from space. And so there are a lot of sophisticated ways of doing this. People have dedicated decades of effort to just this question. Sometimes, though, people still investigate by eye a particularly loud, weird event in the detector. They'll look at that and try to judge, oh, nothing about this makes sense for being a gravitational wave. Did you have any other questions?
So I'm looking at it from a very different perspective. Like, can the gravitational wave be formed due to like changes in mass?
Yes, in principle, anything that there's a certain quantity called the mass quadrupole of a system. It is a measurement of both the mass of the system and how the mass has been deformed away from being spherical. Okay? So a sphere doesn't have, so a sphere has a certain quadrupole moment, but it's not interesting in terms of gravitational waves, but an ellipse or a football has an interesting quadrupole moment. Anything that changes that quadrupole moment, whether it's going up and down in mass, or turning in a circle, or oscillating in and out, generates gravitational waves. Yeah. Okay.
You brought up the question of when you're closer to the point of gravitational waves, like where you can feel them.
Yeah.
Is that related to the inverse square law where you can feel it? Because you said on an order of a billion.
That's a fantastic question. So if you've had a physics class that taught you about gravitational forces, you know that they fall off with the square of distance. So if I move twice as far away, the force falls to a quarter its strength. Waves obey a slightly different law. Anything that's a wave, including electromagnetic waves, they fall off as only 1 over the distance. Now with electromagnetic waves, we don't measure the waves directly, we measure the wave squared. It's something known as the intensity. It's essentially the energy deposition of the wave. And so electromagnetic sources like the sun, they grow dimmer, again, with an inverse square law. So if you move twice as far away, it's 4 times as dim. Gravitational waves don't have this problem. We measure the wave directly, so they fall off as 1 over the distance. This is really exciting in terms of astronomy because if you could make the detector twice as good, you see twice as far out in the universe instead of just a little bit further out to the universe. Yeah?
So in terms of the future, if you map out a lot of these in the next 20 years or so,
yes.
So would a map of the universe through gravitational waves look further out or deeper or richer than the visible light? Or
Great question. So initially, we won't be able to go out further than visible light in terms of these gravitational wave detections because the detectors aren't sensitive enough. But the map may look a little bit different and give us complementary information about the structure of the universe as compared to looking in light and radio and gamma rays. Now, eventually, because of this thing I just mentioned, the fact that you only need to make the detectors twice as good to go twice as far in distance, if we build the very next generation of detectors that we're hoping to build, we can basically see out to distances that are so far away that stars had not yet formed at those distant times in the universe. So basically we can see so far out that there's not light anymore to see. And so then we might learn things that we couldn't learn from looking in visible light.
So in theory, you could go to Big Bang.
Not quite that far, because it turns out that getting that far out is sort of gets very hard. But we can get out maybe to when the cosmic microwave background was produced, which is a very early phase of the universe. All right. Thank you so much. These were amazing questions. I'll stop here.
Let's thank Professor Zimmerman.
Thank you for stopping by today in the Room of Lives. Hope to see you again next time.